Hey guys, hope all of us are doing great. In this specific discussion, we're going to look at the internal energy of an ideal gas, and we're going to consider the case of a gas that is allowed to expand into a vacuum and try to see what aspect or how we can be able to describe the concept of work in this specific case. So therefore, as we had said earlier, we can be able to illustrate or use the first law of thermodynamics using this delta E, which is equivalent to E W given as such. So this is the equation or the first law of thermodynamics, which is being expressed as such. So I've said that, of course, if we try to or consider a case of a gas that is allowed to expand into a vacuum, then the concept of work that we're going to consider in this case that is going to be done is going to be equivalent to zero. And this basically is the case because we're going to expect the external pressure, of course, that is going to be, that should have been worked on to be equivalent to zero. So in this case, we can be able to illustrate the various aspects of energy of an ideal gas that is expanding into a volume, whereby we're going to have this change in internal energy, of course, equivalent to zero, given as such. So therefore, we can be able to conclude in this particular case that the expansion of a gas at a constant temperature, then therefore is going to be experiencing no change in internal energy. And of course, we can be able to have a conclusion then, therefore, that this particular concept of expansion is going to be taking place at a constant temperature. And of course, the internal energy of this ideal gas is going to be independent of its volume. Of course, I've mentioned the case of isothermic or isothermal expansion, whereby we had considered this particular case of a constant temperature in one of our discussions in our previous video. I'm going to put a link of that specific video in the description box, of course, in this particular video. So therefore, we can be able to conclude that if the change in delta is equivalent to zero, we can have a particular version of this equation whereby I've said that if delta E is equivalent to zero, then therefore from the first law of thermodynamics, we're going to have Q equivalent to W. And from the previous discussion we had, we can be able to represent the work that's going to be done by this specific gas, whereby we're going to have a W equivalent to the integral of P dV. That, of course, we had said that if it's expansion, then therefore we're going to have it represented as from volume V1 to V2. So therefore it's going to be the integral between V1 and V2. And we had said that we are going to consider the case of an ideal gas, and therefore we are given an ideal gas equation of PV is equivalent to nRT, whereby we had said that we can be able to represent pressure in terms of RT over V given as such. So for us to find that, we can be able to do a substitution, whereby we are going to have that one given in terms of W is equal for P, then therefore it's going to be nRT over going to be dV. So we're going to take this one and have it W given as nRT, the integral between V2 and V1, and dV over V. So this is going to be, of course, I can be able to bring this one here. So this one had given us from our first discussion, nRT is equivalent to, or the work is equivalent to nRT, the natural log over V2 over V1, given as such. And alternatively, we had said that considering the case of a constant temperature for isothermic expansion, then therefore we are going to consider the aspect of pressure and volume, and we had said that this one's have an inverse proportionality. So another version of this, considering a constant temperature, we can give it in terms of pressure, whereby we are going to have another version for representing work, or what we refer to as Q in this particular case, which is the internal energy, given as the natural, this is an nRT, the natural log of P1 over P2, which is a version of this specific equation. Now, in this case, we can be able to consider an example and try to see how we can be able to represent the internal energy of an ideal gas. Of course, I'm going to read question set, we extract the information from there, and then of course we are going to apply what we have learned in order to come up with the final evaluation of basically what that internal energy entails. So the question reads as such: 0.1 mole of an ideal gas is expanded isothermally at 273 kelvins from 3 decimeter cubed to 5 decimeter cubed. Determining the energy absorbed from the surrounding. So I'm going to extract the information from this specific question. So this is question set 1. So we're going to have a 0.1 mole of an ideal gas. So the value for N is equivalent to 0.1 mole of an ideal gas is expanded isothermally, so which means it's under constant temperature at 200, and so T is equivalent to 273 kelvins from 3 decimeter cubed. So the V1 is equivalent to 3 decimeter cubed to V2, which is equivalent to 5 decimeter cubed. Determining the energy absorbed from the surrounding. So we are requested to find the value of Q, of course, which is absorbed from the surrounding. And I've said Q is the same as work, which is nRT, the natural log of V2 over V1 given as such. So doing a substitution for this, we're going to have the value of N given as 0.1 moles times 8.314. So that's going to be the value of R, and then we're going to have the value of T, 273, and then the natural log of 5 over 3 given as such. So doing an evaluation for the internal energy Q, this is going to give me, you can do an evaluation and check. In case you find a different value, then therefore we can be able to note that one in the comment section. So this is going to give me 115.94 joules given as such. So this is how we can be able to directly apply this particular conversion for the internal energy, whereby the delta E, or the change in internal energy for an ideal gas expanding in a vacuum, is equivalent to 0, since it's not having external pressure that is acting upon it. So we're going to see that the heat or the internal energy can be able to be represented using this, or the heat absorbed using this specific formula, and doing a substitution given the information, that we can be able to do an evaluation of a question set over that similar topic. So therefore, this is how we can be able to achieve this, and we're going to use various forms or various examples in trying to solve a number of questions which basically are going to entail the similar topic. So that is it for now, guys. Bye, God bless you. Catch us in our next video.